Okay, so we are now going to start the exercises of this last section. Now before we look at the first exercise and its solution, it becomes necessary for us to first address one issue that we came across when a polynomial ring in several variables was defined. So let's recall that definition and let's see that issue also once more. We start with a commutative ring with unit element. Then Rx1 is our usual polynomial ring in the indeterminate x1 where the coefficients are coming from the ring R. Just like Fx1 is a ring where F is some field, Rx1 is also a ring. And in fact, Rx1 itself is a commutative ring with unit element. And that fact actually gives rise to the idea of introducing more variables, because this is a ring with these properties, this is again such a ring with those same properties, then why not keep doing it? So you introduce another variable, and this by definition is the polynomial ring in the indeterminate x2 over this, which itself is a commutative ring with unit element. So once you convince yourself that when R is a commutative ring with unit element, then so is Rx1, then from that itself it follows that this is also a commutative ring with unit element, and the process goes on. And that's how we get to a general polynomial ring with n indeterminates or n variables. Now we have already seen, we have discussed this before, in fact using one example, that the elements in such a ring can be quite complicated. For example, if you think of an element in this ring in the second stage, then such an element looks like this. F1, x1, x2, f2, x1, x2 square, fn, x1, x2 to the power n, where these fi's, each one of them is itself a polynomial in x1 over the ring R. Now in the text, the author simply said that the elements in such a ring look like this. It's a finite sum where these a's are coming from R, and these are of course the indeterminates, and the ij's are non-negative integers. Why is it true? It's not immediately apparent that this is true. In fact, when we discussed this about this using that example, we saw that if we write expressions for all these polynomials and then we perform multiplication and then consider everything together, eventually we end up with an expression with a sum like this. However, that is just one vague way of looking at the thing, which is not rigorous, and that is also only one example. Okay, so to see all the things rigorously, we are now going to look at this special exercise where what we will do, let us first see what the exercise says. For a commutative ring R with unit element, construct a ring to distinguish it from the ring we already have. I am using star. Just like this polynomial ring, but without using the recursive definition given in the text, such that these two rings are isomorphic. By that, what we really mean is this: we will define this ring to be the set of all formal symbols of this form. In that set, we will define an addition and multiplication, show that the resulting system is a ring, and then we will show that that ring is actually isomorphic to this. Once we prove this fact, then Herstein's remarks will be rigorous. I mean, it will be justified. Okay, so let us see how to proceed with this task. For convenience, in the beginning itself, we denote by A the set of all non-negative integers. In this book, N denotes the set of all natural numbers, and natural numbers start with 1. So that's the reason we had to give a name to this set. Define R x1, x2, etc. to xn star to be the R is already known. Okay, R is some commutative ring with unit element, that is given. So we define this to be the set of all formal symbols that look like this. We can't be that vague like the text. We have to be absolutely specific about these symbols. So to avoid notational confusion, we use comma in between. That is one thing. And we have to also say what these ij's are. I1, I2, etc. to in, this vector, we are using an ordered n tuple because order matters. If the order changes, then the corresponding term also is something different. If you change the order of I1 and In only, say, then you have In here and I1 here. If they are different non-negative integers, then the term becomes different. So that's why an ordered n tuple, and it is belonging to An. So this is a formal sum where each term is coming for one such n tuple. But there is one more thing we have to mention here, where this is, of course, it has to be mentioned that this belongs to R for all n vectors belonging to An, and note that A is an infinite set. So an, which consists of all n tuples of elements of A, is also an infinite set. But we don't want an expression where there are infinitely many terms having non-zero coefficients. So we have to carefully mention that in any such formal symbol, at most finitely many coefficients are non-zero, and a I1, I2, etc. up to In is not equal to 0 for at most finitely many vectors it is the same as saying that, say you have a polynomial in a single variable. You denote the polynomial, here say you have I belonging to A, which is A1. I belonging to A means I is a non-negative integer. So when I is 0, you have A naught x to the power 0. When plus I is 1, A1 x to the power 1, and so on. But to make it a polynomial, you have to mention that at most finitely many terms are non-zero, so that in the expression effectively there are only finitely many terms to work with. Okay, so the same thing is true here, only the dimension is higher. Okay, now in this set of formal symbols, we are going to first of all define equality. When are we going to say that two such formal symbols are equal? Yeah, we have to first define equality. For two elements since the notation for these symbols is quite cumbersome, we have to we cannot further simplify it. We have to mention these things. So we have to be careful about what we are writing. This and bi1 to in in we declare that they are equal, that is these two things are equal, are defined to be equal. If and only if the corresponding coefficients are equal. You will see that the things are almost like the single variable case, only the notations make them look extremely difficult and extremely intimidating. The underlying things are similar. If and only if ai1, i2 up to in is equal to in, for all n vectors this. We now define addition and multiplication in this set as follows. We are now going to add two such symbols and multiply them. Addition will be quite straightforward. Multiplication is a little bit difficult, but we will take our cue from the single variable case. in Can I write it here? Okay, then no need to clutter the space unnecessarily. Let's take enough space and write the things clearly. By definition, this is equal to plus b I1 no matter how complicated these A's and B's look, after all they are elements in the original ring R. So this addition is that in R, is the addition we have in R. And the product of these polynomials here I am using j's, why you probably already know. It's that when you define the product of two polynomials in a single variable, there also if you go to that definition, you see that we use I, j and k because of the nature of the definition. B, j1, but it does not matter whether you use j or I. After all, these are dummy variables, so you can use anything. What values they take, that matters. Jn x1 to the power j1, x2 to the power j2, like that up to xn to the power jn. And this product is it's going to look quite complicated, but keep in mind that it has come from the single variable case. It's motivated by that case. K1, K2 up to Kn belonging to An. Summation I alpha plus j alpha is equal to K alpha. Alpha varies from 1 to n. Ai, okay, we are taking alpha, no? So that means there also we have to take alpha. Oh, because alpha is varying from 1 to n, fine. B, j1, j2 up to jn, and with that we have this. Okay, so that is the definition. You can see that this definition reduces to the definition of multiplication when we have only one variable, that is when n is equal to 1. You can clearly see that from here. If n is equal to 1, then we have only k1, and k1 varying over a1 means k1 is varying from 0 to infinity over the integers. Here you will have I1 plus j1 equal to k1. You won't have any alpha because there is only one index 1. ai1 bj1 x to the power k1, that is let me just write it. It will look like this. I1 plus j1 equal to k1, ai1 bj1 x1 to the power k1. So now you can see that it's just the definition of multiplication for two univariate polynomials where the indeterminate is only 1, x1. Okay. Now, having defined addition and multiplication, note one thing, that the way we define these formal symbols, we are allowing these vectors, that is the multiple indices, to vary over this finite set, but to make matters, vary over this infinite set. But to make matters finite, we have also imposed the extra condition that at most finitely many coefficients are non-zero. Now, is that condition also true for these results of these operations? note that since the finitely many a's are non-zero and at most finitely many b's are non-zero, so at most finitely many a's plus b's will be non-zero, because using only finitely many a's and finitely many b's, if you add them up that are non-zero, at most finitely many non-zero a plus b's can be produced. In fact, the number of non-zero a plus b's may be smaller than the original number of non-zero a's as well as non-zero b's. That is because it may happen that this a, suppose, is equal to minus b, so that the sum becomes 0. In any case, you can never produce infinitely many non-zero a plus b's from finitely many non-zero a's and finitely many non-zero b's. So that is the case of addition, and the same is also true for multiplication, where the coefficients are more complicated than addition, but still we are using only finitely many non-zero a's and finitely many non-zero b's, right? So we are going to mention that. One can verify that these operations are well defined. Note that not equal to 0 or at most finitely many vectors in an, and if you want, you can write these conditions in a single line separated by a comma. If I don't have much horizontal space, so I am writing like this. Only the conditions should be there. However, I have not seen anywhere a notation where someone is writing one portion of the condition below this summation symbol and one portion above. That I have not seen. Whatever conditions we have that is restricting the sum, usually they appear below the summation symbol. Okay, and we are now saying that this is also not equal to 0 for at most finitely many vectors in fact, not only are these operations well defined, but one can almost immediately see that our set of these formal symbols is an abelian group with respect to this addition. Because we have defined addition component wise, so as far as addition is concerned, things are actually quite straightforward, despite the quite horrendous look of these symbols. Also, one can easily see that R, let me write it in the next line, is an abelian group with respect to this addition. Okay, so this is an abelian group, but we want to prove that it's in fact a ring with respect to this addition and that multiplication. For that, we have to actually verify the distributive law and the associative law for multiplication, unfortunately, but it has to be done. So for that, we considered three elements. A equal to summation this is one element, this is another, and a third element, C. in our set. We are first going to verify that multiplication is associative. Now, okay, so we start the big calculations. AB, first we calculate AB times C. In this step itself, we write the expression for AB. So this is A, this is B. You think of those J and you go back to the definition. This gives us K1, K2 up to Kn belonging to An. Shall I be able to write it here? That's the question. let me fully use this much space as well as that part also. I mean, I can't possibly write everything in this small confine. I alpha plus j alpha equal to k alpha, where alpha varies from 1 to n. Let me continue from there. Summation of what? Summation of a I1 I2 up to In times b j1 j2 up to jn. k1 k2 up to kn. This is only AB times C. So you can see how complicated it will become, but let's proceed carefully. Now if we write the formula for C, for the final product, what shall we get? I have all the things written here so that I don't make a mistake. Let me just copy this step because I think I'm already going to mess up. Okay. M1, M2, so we will be adding the exponent of say x1 here and here. So I1 plus k1. Okay. So that means summation I alpha plus k alpha equal to m alpha. Alpha as usual varies from 1 through n. But then inside we have this. And this is, no wait, I1, I should not write I1 plus K1 because the K's are appearing before C. I, of course, I cannot write. K alpha plus say L alpha. Yes. Now K alpha itself is the sum of I alpha and J alpha. Okay. And we of course have this term A I1 I2 up to In B J1 J2 up to Jn, but then we have to multiply the term of C that is arising because of these L alphas. That means C1, what am I writing? CL1 L2 up to Ln. That means we are multiplying this inner sum, not, excluding this one, excluding the xi's, the inner sum, which after all is an element in the ring R, we are multiplying that by this, and such products are being added according to this rule of this outer sum, I mean the intermediate sum. The absolute outer sum is there, that we let's not think about it for a moment. So we have multiplied this thing by C, and we are taking sums of such products. Okay, and outside, now outside we have to write the xi's, but now for the xi's the exponents are mi's, which are sums of k alphas and l alphas. So this bracket is has been closed, this one has been closed. Now outside we have this. Now because each k alpha is I alpha plus j alpha, and since we have double summation, we can write it as a single sum where we vary everything according to how they are already varying. It's just another way of writing the same thing. A sum of sums is after all a sum. What that final sum is, that you have to carefully write, but after all it's a sum. So this is equal to an. Now we will write summation I alpha plus j alpha plus L alpha equal to m alpha. We can apply the distributive law in R. Note that this is a sum and outside we have this C, so we can multiply each term of this innermost sum by that C, and we can write the sum, that is this sum, and its terms look like this. C L1 Ln. Now just like we have been able to write this double sum as a single sum, we can again write this single sum as a double sum, but not the exact same thing, something else. In this entire variation of these vectors, I alphas, j alphas, L alpha, and in having this very large sum, you can do one thing. You see, we have applied the distributive law to multiply all the terms in the inner sum by these Ci's. Now what we can do, say you have some fixed values of I1, I2 up to In, okay, and say the j alpha and L alphas are varying, so that the sum of I alpha, j alpha and L alpha is actually equal to m alpha. So the thing here is this, say I alpha is some value. For once you think that I alpha is some fixed value, some fixed non-negative integer, then I alpha is fixed, m alpha is fixed. I mean, for a given mi here. M alpha is fixed, I alpha is fixed. Now keeping them fixed, we can in fact change J alpha and L alpha. Say you can increase J alpha by 1, simultaneously decrease L alpha by 1, so that the sum remains constantly M alpha minus I alpha. Okay, that you can do. So what I am trying to say is that you will find some A's that will appear in many such terms in this sum. You can take them common out. That will give you again a double sum like this, and we will get this. This belongs to an summation I alpha plus P alpha. Yes, we can call it P alpha. I alpha plus P alpha equal to M alpha. Alpha varies from 1 to M. In. Inside you have the other summation where J alpha plus L alpha is equal to P alpha. Okay. And the terms of course are the same, they have the same form. So we have taken these A's common out from the terms where that same A appears, and we have written the sum of such terms where A's are common. Okay, so together they have been written as terms in this intermediate sum. Okay, now it's sort of doing back calculation. We have come to this central step, then we are going back in the sense of applying the steps. First we expanded all the sums and expanded all the products by multiplying terms out, and then we are taking things common out, and now we are going to again write a product of some sums. Now this becomes equal to, if you look at the structure of this product, then it is actually equal to A times this J alpha plus L alpha equal to P alpha. So that means here we have P alpha. So P1, am I getting it correctly? Yes. Never lose track of what we are doing. Okay, once you lose track, then everything is gone. These are just some abstract symbols. It is equal to this summation J alpha plus L, that continues to be true. J alpha plus L alpha is equal to P alpha, and alpha varies from 1 to n, and we still have this. Let me write it here. B J1 J2 up to Jn, C L1 L2 up to Ln, and if you go to the definition of multiplication, you multiply A with this formal sum or formal symbol, you are going to get this one. It's like just this step, only in the reverse order. And if you look at the definition of multiplication once more, this part except A, this part is the product B, C. So this is equal to A, B, C. So multiplication is actually associative. And this one is not this difficult. We don't have to deal with multiplying 2 times in a row. I mean, the distributive law that we are now going to show, it involves only multiplying once. A times B plus C, you have to multiply A and B, A and C, and A with B plus C, and see that they are equal. So we start with the expression for A times B plus C. A we keep just like that. For B we write B plus C, so it's going to be B J1 J2 up to Jn plus C xn to the power Jn. Now we have to perform the multiplication. That's why I am using J. I alpha plus J alpha is equal to K alpha A I1 I2 up to In times So here we don't have space to write, make another line, so I am using comma. And this is just going to be a use of ordinary distributive law that we have in the ring R. So we will write in b j1 j2 up to jn plus c So here we are applying the definition of addition in our system, in our set of formal symbols. Kn belongs to an C j1 j2 up to jn. And if you look at the form of these terms, this is nothing but AB and this is nothing but AC. So this is equal to AB plus AC. Also, since the multiplication is easily, in fact this is easy, it's easy to see that the multiplication is commutative. So because of commutativity of multiplication, not only is the left distributive law true, but the right distributive law is also true. That is, A plus B times C is also equal to AB plus AC. So we have in fact proved that the set of formal symbols that we have defined along with the addition and multiplication that we defined is a commutative ring. Thus, This is a commutative ring with respect to the addition and multiplication defined above. Now define the element delta I1, I2 up to In in the ring R to be equal to 1 if all these ij's are equal to 0 and 0 otherwise. That means for any n tuple of elements in a to the power n, we are defining an element in the ring R which we are denoting by this symbol, and its value is 1 if these are all equal to 0. That means for the 0 tuple where all the components are 0, this element in the ring R is the unit element 1. Note that R is given to be a commutative ring with unit element, so this is that unit element. And for any other n tuple where at least one ij is non-zero, the value of this corresponding delta is 0. One can verify that the element in our set of formal symbols, which now we can call it a ring because we have shown that it's a ring. This symbol acts, this element acts as a unit element. So our ring also has a unit element. Okay, now comes the difficult job of showing that this ring, which also is a commutative ring with unit element, is isomorphic to the our original polynomial ring. We now show that this ring is isomorphic to the original polynomial ring. How can we do that? For that, it will be helpful to write the formal symbols in our ring as some actual sums. Actual sums means sum of some elements in this ring, where the sum is actually the addition we have defined in this system. And specifically, we are going to do this. Consider, let me just feed it some ink. So consider the element in any general element. In our ring. For each j lying between 1 and n, we are going to define a formal symbol related to that j in our ring of formal symbols. We define these elements: x j star to be the element summation alpha j I1 I2 up to In where alpha j In is defined to be equal to space 1 if ij is equal to 1 and I1, I2, that means all the alphas are equal to 0 except the jth I, that is equal to 1. Ij minus 1 is equal to ij plus 1. In is equal to 0 and 0 otherwise. You may wonder about this multiple suffix. Here, besides having the I alphas, we have an extra j also. That we are doing just to show that this entire coefficient depends not only on the I alphas but also on j, because its definition involves j, it uses j, that's why. Okay, now with these elements, now these are again formal symbols, so they are elements in the ring. One can carefully note that using the definition of addition and multiplication that we already have in this ring, we can now write such a formal symbol as an actual sum, and that's what we are going to write. It's easy to see. It's easy to see that this formal symbol is equal to this actual sum. Note that the sum on the right side is actually a sum of some elements in our ring. The interpretations of this sum and this sum are entirely different. The interpretation of this sum is just it's a formal symbol that as a whole is an element in this ring. However, in this sum, everything has a meaning of its own. This x1 star is this element when we have j equal to 1. Here we are taking the I1th power of x1 star, which makes sense because in calculating the I1th power we will be using the multiplication available in this ring. Again, these powers have been multiplied. There also we are using multiplication. We are multiplying such a product by this. By this means this, you can ask me, this is a ring element. This is an element in the original ring R. However, this is an element in this ring. So what is the meaning of this multiplication? That we are multiplying an ordinary element of R with this. That multiplication is nothing but the multiplication of this product in this ring and again an element of this ring, which is okay, what can I say about that? What I am trying to say is that this corresponds to an element in this ring, and that element is actually the element where you have the identity, you have the unit element. We have the unit element in this. From the unit element, using this ring element, you can create an element. I think I hope you know what I am talking about. Do I have to say it specifically? The situation is so complicated. This is an ordinary ring element. okay, and we have the unit elements, say I am denoting it by I in this ring, whose definition uses those deltas. Now in that you multiply okay, so this is the element that I am talking about. This element, if you multiply this element with this product, you will get this thing, and the sum of such elements, where the sum is actually the sum that we have in this. Now it may seem like I am trying to say something extremely non-trivial here by just simply saying that it's easy to see that this becomes equal to this. But if you, what I want you to do is that I want you to say take x1 star, actual x1 star, okay, calculate its square, then multiply that with this type of element and see what you get. You play with these symbols, or what I am trying to actually say is this: you take a concrete element in the ring of this form, don't dilute n, okay, keep n as n, you take some special values here, and then you try to see how this is actually equal to this. In doing so, you will see that really the thing is very easy. All the things follow from the definitions of addition and multiplication. It looks complicated, but actually it's quite easy. It's in fact so easy that once you get the point, you will see that yes, we can write it like this. So before you do that, you have to take my word for it that this can be done. And we are going to mention this fact. The sum on the right side is an actual sum of elements of our ring. Hence, now here comes the crucial observation. So you can write this element like this. because it's an expression where the sum and product are the ones we have in our ring. So what we can do, we can take xn star to the power in common out from those values that are the same for this in the terms. In some terms it will be the same, so we take those things common out and write the whatever is left inside, and that gives us one term. So the entire sum can be written as a sum of such a finite number of such terms. Okay, now you look at this final expression. Doesn't it look like a polynomial in xn star where the coefficients are polynomials in the remaining n minus 1 variables? It looks like just like that. So the elements of our original ring that we constructed can be thought of or look like elements in elements of this star xn. A polynomial in xn, actually I should write x1 star xn star, but you get the point. The thing here is that what name we give this variable, that does not matter. The name does not matter. I can call it z also or y also. The operations matter, and where the coefficients are coming from, that matters. Okay, so this looks like a polynomial in xn star or some other variable xn where the coefficients are elements in this, which is again a ring like this, only the number of variables is less by 1. And this is the observation that will help us in setting up that isomorphism. To turn this look like into an isomorphism, we take another element like this and expressed in this form. we are now going to add these two elements according to the addition that we have defined in our ring. That is one thing, and at the same time we are going to also add these expressions as if we are adding two elements in this ring, where also we are going to add elements of this ring, but using ring properties, that addition is commutative, associative, those things, and we will see that these two things actually match. Match means, of course they will match because they are equal, but the sense in which they will match, that is important. If you add these two polynomials according to the definition of addition we have in this ring, and then turn that sum in this form into this form, you will get something. On the other hand, if you add this expression with this expression by using the properties we have in this ring, that is in general in a ring, whatever ring axioms we have, using those axioms you add these two, then also you will get that same expression, as if you are adding two elements of this. When you are adding this expression with this expression, you can view your addition as happening in this ring, okay, which is a polynomial ring in Xn, where the coefficients are coming from here. So that is why, we have to show both the cases, that addition and multiplication behave exactly similarly, and that similarity will give rise to an isomorphism between this ring and this ring. Then using this isomorphism we will be able to finally show that this ring is isomorphic to our original initial ring. So for that, let us start the addition. Now summation okay. The first step is just the definition of addition. Now we express this in that form. It will then be equal to in belonging to A summation times So this can be written as a in belongs to a summation a I1 I2 up to in 1 to the power I1 x2 to the power I2. Oh, I should not forget star I n minus 1. Plus here this is just the sum of two elements, that is this sum is the sum of two elements in this ring. Okay, and you can see that this thing is equal to the sum of two polynomials this is one polynomial and this is another polynomial. Two polynomials in here keeping in mind that this xn is the same as xn star, whatever we call it, the name does not matter, just a variable is there. So you can see that whether you think of these formal symbols as formal symbols or as elements here, the sum, the structure of the sum is not affected. The sum is actually preserved. It does not matter whether you think of them as formal symbols in our original ring or as symbols or elements in this ring, this polynomial ring, as far as addition is concerned. So let's write accordingly. As we do the calculations, let's also, after each such calculation, we interpret it properly and we write the interpretation. Hence, we can think of an element in this as an element in this as far as addition is concerned. Next, we calculate the product of these two elements. Because of product, we are using J. So first we apply the definition of product and then we will modify it accordingly. K1, K2 up to Kn summation I alpha plus J alpha equal to K alpha times at one point I thought, before making today's video, I thought that in this small space I won't be able to carry out such big calculations, but now I see that we just have to carefully keep track of all the things, that's all. The length of the calculation does not matter really. Now we write this final abstract symbol or formal symbol in that form using those stars. In belongs to A, summation, oh it's not in, see, a mistake, Kn belongs to A, summation K1 K2 up to Kn minus 1 belongs to A n minus 1. Okay, inside that still we have summation, so two summations. I alpha plus j alpha equal to k alpha, and alpha varies from 1 to n. Of what? Of these terms. Close this summation and write close that summation, the intermediate one, and outside we have this. Okay. Okay, now because we are varying Kn over A, and here K alpha is appearing as I alpha plus J alpha. So for alpha equal to n, for that specific value of alpha, we can bring out another summation depending on Kn, because the outermost variable is Kn. So in place of this we can write like this: summation Kn varying over A, then summation I1 plus K1, In plus Kn, or In plus what the hell am I saying? In plus Jn is equal to Kn. Yes. Then inside summation K1 K2 up to Kn minus 1 varying over An minus 1. Then inside of that still summation I alpha plus J alpha is equal to K alpha, but because we have taken this outside, alpha no longer varies from 1 to n, but from 1 to n minus 1. And inside this we have okay, so this times x1 star to the power I1, x2 star to the power I2 up to xn minus 1 star to the power In minus 1, xn star to the power In. 1 2 3 1 2 3. Yes. So in this step, what is it that we have actually done? We have just written this sum, this innermost sum. I mean, what can I say? As a sum of these terms and a sum of sums, because do you realize what these conditions are saying? Here for example, here all the n equations are simultaneously true. One condition we have taken separately and written outside. Okay, that we can do, because after all everything is going to be added up. And in doing so, here we have reduced the variation of alpha, I mean the number of choices for alpha, by 1. So that's what we have done here. Okay. Now this becomes equal to, the outermost sum remains as it is. After that, this sum also remains just like that. In plus kn plus jn equal to kn, and then this thing means this. If I use a slightly different bracket, say I use this, thing, the expression inside the curly brackets is this product. Summation. I think at this point it's better to copy, because otherwise already things are going out of my hand. Let me first write and then we will try to make sense of it. In x1 star to the power I1 up to xn minus 1 star to the power in minus 1. This is one element, and this is another element, b j1 j2 up to jn n minus 1. Have I been writing in? If so, then I think I have done a mistake. these are not in, these are kn. Please rectify this. Here also I have written it wrongly. From this step it is kn, because you can understand we have the k's. So this is kn. So what is the meaning of this sum? Kn is varying over a, fine. For a given value of kn, say kn equal to 1 or kn equal to 10, you then consider all non-negative integers in and jn such that their sum is 10. For that, you will get this entire thing, where you will vary this I1, I2, etc. also over each one of them over a, and here you will vary the j's over a according to, of course, what is given to us, because these a and b's are they have already been chosen before. They are coming from the two elements that we considered of whose product we are calculating right now. And okay. Oh, so I was thinking of how these values of in and jn are affecting the inside, because they are used in the choices of these coefficients. So that's how they influence the thing inside. Fine. Now, is this product actually equal to this? Yes, it is, because we are just simply applying the formula for product of, say, two polynomials in these, that is, we are in calculating this product, this times this, that is this product, we are using the definition of multiplication in this. Okay, so that if you do that, you will directly get, in fact, that is the formula, that you get this and the coefficients are this and the variable part is this. And finally, this entire thing is actually this product, summation in belonging to a summation I1, I2 up to in minus 1 belonging to an minus 1 a I1, I2 up to in x1 star to the power I1, etc. up to xn minus 1 star to the power in minus 1 times xn star to the power, oh, here I have in, okay. This thing which is which can be considered as a polynomial in xn star with coefficients coming from that ring where we have n minus 1 variables, times this. Jn belonging to a bj1. Oh man, all these things are really looking like out of this world mathematics. but you can understand that the underlying things are quite simple. These equations will look nice if they are written on long boards. x1 star to the power j1, xn minus 1 star to the power jn minus 1, xn star to the power jn. So whether we think of the elements as formal symbols or as polynomials in xn star with coefficients looking like this, if we take their product, the product remains the same. So the product structure is also preserved. So we can think of an element of this as an element of this. What should I write? Multiplication also does not create a problem. Element of this as far as multiplication is concerned. Maybe this is not a very good way of writing it. You understand what my point, what I am trying to get across, that this transition between the interpretations of the elements in two different ways, this does not affect addition and multiplication. In that sense, nothing changes actually. So, because of this, these two rings are actually isomorphic. Star xn. This denotes the fact that the rings are isomorphic. Now, using this insight, we are going to prove, we now prove this. By induction on n. The case n equal to 1 is trivial because there we don't in fact have to apply any recursion, the recursive definition that we have for our original ring. The case n equal to 1 is trivially true. Assume that this is isomorphic to this. For some positive integer, then the original polynomial ring. By definition, this is not just isomorphic, this is in fact equal to this. And this is isomorphic to this, so that means the larger polynomial ring over this new variable xn plus 1, they will also be isomorphic. And by what we have proved here, this is isomorphic to this. So that completes this horrible solution. But now we can say for sure that yes, the elements of our original polynomial ring are such sums where the terms look like this. Okay, so here I end the video. Now armed with this thing, we will in the next video we will actually start solving the exercises. If you have any doubt regarding this thing, don't comment. I'm just joking. You can always comment in the comment section, or you can mail me to the address that I provided. So with that, I sign off for tonight. This is me, Lucifer, from a mathematical room. Have a nice night.